So today we're going to go over the discussion for our ramp lab motion on an incline. We're going to focus right now on page 32 in the lab notebook. In our class, we're going to start taking notes on this on September 10th, 9/10. Now you can go with this title, lab ramp motion on an incline, or you can use the title that will be in our table of contents, which is going to be ramp lab position versus time discussion. This is going to serve as a way for us to discuss what we did in the first part of this lab for our position versus time. Now, we're going to start off this discussion by looking at our two labs. During the last lab, we had a graphical and mathematical relationship between position and time, but we're going to focus on the graphical relationship first. The graphical relationship is what I have right up here, where I drew my position versus time graph, and I just had like a very simple way to represent our two relationships. As time increases, so too does our position. And one thing that we saw was this was going to be a linear and direct relationship if we had a starting position of 0 meters. So we could say that our position is directly proportional to our time. Now this is going to be a great way to represent our data when we know the fact that our velocity is constant, which is what I'm going to have written down underneath my graph for the buggy lab. What that means is our velocity is going to be equal to our displacement, the change in position, over that time interval, the change in time. That velocity, which is equal to displacement over the change in time, is going to work for the entire time interval of the graph. That velocity is the same here on the graph as it is up here, here, here. The entire graph has one constant slope, so we can assume that the velocity will be constant. One thing that we saw in the first part of our ramp lab is the fact that our slope is not going to be constant. We ended up having this curved line over here on the right where we have our ramp lab, where once we connected those data points, it looked like it was going to be curved. What that means is our velocity is going to constantly be changing. Our velocity down here is going to be much, much lower than our velocity all the way up here, which does kind of make sense based on what we were seeing in the lab. Our velocity was increasing as time went on. So after we have our graph written down for our ramp lab, where we have our position on the y-axis, our time on the x-axis, and we're showing this exponential relationship, where position is proportional to the square of the time values, then we can talk about what that means. Our velocity is not going to be constant. And if our velocity, which is the change in position over change in time, does not accurately represent the, cart at any point, we can't really use that relationship for this graph up here for our ramp lab. We're going to need to find a way to, make sense of what that means. And that's what these dashed lines over here and all these little delta t's and delta x's really means, is a way for us to talk about what that is going to look like and what we can do with that. So the top of our page, page 32, we should have our title, date, and page number. And then at this point, we should have our buggy lab, that graph that is showing that linear relationship, and a couple bullet points. The first saying that our velocity is constant. The second saying that our velocity is equal to the change in position over change in time, and that works for the entire time interval of the graph. The other thing that we should have at the top of this page is our graph for the ramp lab. This is just going to be a simplified view. Instead of that full sheet of paper that we have taped onto page 31, it's just going to be a very simplistic way to represent this relationship, where position is proportional to the square of time. And then the two bullet points we'll have beneath that is that the velocity is not constant in our time interval. So the velocity, which equals our change in position over change in time, does not accurately describe the velocity at a given time, because at a given time, the velocity is always going to be different. So underneath that, we're going to have a few more graphs that we're going to draw. So I'm going to be drawing that same graph from our ramp lab 3 times, where I have that, well, same curve for all 3 of these. But one thing that you might notice is that I'm going to have these dashed lines. What this means is if I were to have a, well, solid line connecting where I begin with where I end, that right here can represent our average velocity in that entire time region. However, that's not going to be a very good representation of motion. So instead of having it go for our entire time region, one thing that we can do to try and make it look a little bit easier for us to figure it out is to just focus on a smaller region. That's what this dashed line is going to be. If I shorten the amount of, well, both position and time that I'm looking for, a smaller time interval, I still have my average velocity. However, that average velocity is not representing the entire region. It's only representing, well, from wherever this point is right here up to here for our time 1 and time 2. And that's representing our position 1 and position 2. It's going to be a better way to represent our data in that region of the graph. But we can even take this a step further. In the second graph, it looks like I ended up making it even shorter for that time intervals, where instead of having a nice big time interval, we're shortening what those 2 times are, which also means our change in position is going to be even shorter. So when we connect these 2 points, it's going to be a much smaller line, and the slope is going to change, which means our average velocity of that line is going to change. But it's going to more accurately represent our average velocity, or really the velocity at that region. This final graph over here on the right, I've shrunk that time and our position interval even smaller. Our time 1 and our time 2 correspond to our position 1 and our position 2. So when we are connecting those 2 points, it looks like it's basically just connecting the curve, where we can barely see any of that, well, blank space between where our curve is and the line of best fit between those 2 points. So when we're showing this change in position and change in time here, it's doing a really good job of representing the velocity in that region. It's still not going to be absolutely perfect, but it is a way for us to get a little bit closer. So after we have those graphs drawn, and we are showing what those relationships could be just by having our time 1 and time 2 corresponds to those change in times, and our position 1, position 2 corresponds to that change in position, we can talk about this bullet point that I'm going to have right underneath these 3 graphs. What this bullet point says: shrinking the time interval, the delta t, allows the calculated average, our v velocity with a bar on top of it, to more closely resemble the curve. As we continuously shrink and shrink that time interval and subsequently our position interval, that curve and that line that is connecting those 2 points is going to shrink to basically, well, no time and no change in position, and that will be a really good way to represent almost instantaneously what the velocity is at that point. So we're going to continue with that, where we're going to take an even smaller time region and position region here, which is very similar to the one we had just above it. And we're going to assume that as our change in time is getting smaller and smaller, eventually that's just going to line up with a single curve that kind of goes through that one single point, which can be very similar to the one that we are seeing over here, where it's only touching the curve at that one point. So after we have these next 2 graphs where we are showing that as we are decreasing that time interval between our 2 positions, we're seeing that the velocity is almost becoming instantaneously, we can have these 2 points. A very small change in time is a reasonable estimate of how fast an object is moving at any given instant. As that change in time approaches 0 seconds, this line becomes a tangent line, which is the instantaneous velocity at that time. So while we definitely can't say for a fact, hey, I know this point right over here, I know exactly what that change in time is and what that position is right there, one thing that we can say is we do know there will be a point right here. And if we know what that line is, where it's only touching that single point, we can try to use another point on that line itself in order to figure out, well, what that second time is and what that second position is going to be. So once we have that line of best fit, that is basically going to be our tangent. It's just a line that is touching your curve at a single point. We can use the point where it is touching our curve, which I'm going to have as x1 and t1. And then I'm going to use a second time and a second position. If we know that, then we can calculate the slope of this line, which is going to be the velocity of that line, and that will be our change in position over our change in time. x2 minus x1 for those two positions on the y-axis, and time 2 and time 1. That way we can find out what that velocity is going to be. So this is our velocity that is going to be our instantaneous, our velocity at that specific point. Now, it won't be exactly perfect, but one thing that we can say is this is going to be a reasonable estimate of how fast an object is moving. If we know what those 2 points could be, either on the curve itself, or if we draw a tangent line, we can end up figuring out a reasonable estimate of how fast an object is moving at any given instant, or our instantaneous velocity.